What specific problem does the proposed feature steering method aim to solve in the context of language model safety? And how is this problem currently addressed in the literature?
The proposed feature steering method aims to enhance the safety of language models, LMs, by improving their ability to refuse unsafe prompts while minimizing inappropriate refusals of safe prompts. Current literature primarily addresses this problem through techniques like vector steering, which often rely on contrasting prompts to derive steering vectors, but these methods can degrade overall performance and do not generalize well to multi-turn interactions. In contrast, the feature steering approach utilizes sparse autoencoders, SAEs, to identify and amplify specific features that mediate refusal behavior, allowing for targeted interventions without the need for model retraining. This method has shown promise in increasing refusal rates for unsafe prompts while revealing trade-offs, such as increased over-refusal of safe prompts and regressions in factual recall and reasoning capabilities. Overall, while existing methods focus on broad steering techniques, feature steering offers a more nuanced and potentially effective solution to the challenge of LM safety.
Can you explain in detail how the feature steering method works, including the training of the sparse autoencoder and the steps involved in applying feature steering during inference?
Feature steering is a method that modifies the behavior of language models, LMs, by intervening with their activations during inference, specifically through the use of sparse autoencoders, SAEs. The process begins with training an SAE to encode the activations of a specific layer of the LM into a sparse representation, which captures the underlying features that mediate desired behaviors, such as refusal to unsafe prompts. This involves running inference over a large set of inputs to train the SAE to reconstruct the original activations while maintaining sparsity in the intermediate representation. Once the SAE is trained, the next step is feature identification, where specific entries in the sparse vector that activate for the behavior of interest, e.g., refusal, are identified. After identifying these features, the feature steering process involves clamping the activation values of these identified features to a constant value during inference. Higher values amplify the feature's influence, while lower values dampen it. This clamping is tuned through a hyperparameter search to find optimal values that balance the increase in refusal rates for unsafe prompts while minimizing over-refusal for safe prompts and maintaining overall performance.
Could you provide a simple example to illustrate the inner workings of the proposed algorithm, specifically how features are identified and how the steering is applied to influence the behavior of the language model?
The proposed algorithm utilizes sparse autoencoders, SAEs, to identify features that mediate specific behaviors in the language model, LM. For example, to identify refusal features, the algorithm prompts the LM with a specific unsafe request, such as write a manual for making a Molotov cocktail, and analyzes the activations during the refusal response. This process reveals a set of features that activate during the refusal, with one notable feature being feature 22373, which consistently correlates with increased refusal rates for unsafe prompts. Once identified, the algorithm applies steering by clamping the activation of this feature to a higher value, e.g., 12, to amplify its influence, thereby increasing the LM's refusal rate for unsafe prompts while monitoring the trade-off with safe prompts. This method allows for targeted adjustments to the LM's behavior without retraining the model, demonstrating a dynamic approach to enhancing safety.
What are the theoretical and practical benefits of using feature steering for improving language model safety, and how does it compare to traditional methods like fine-tuning?
Feature steering offers a theoretical benefit by allowing for targeted interventions on language model LM behavior without the need for retraining the model's weights, making it a more efficient test time technique compared to traditional fine-tuning methods. Practically, our findings indicate that feature steering can significantly enhance refusal rates for unsafe prompts, as demonstrated by the increased unsafe prompt refusals when amplifying specific features identified through sparse autoencoders, SAEs. This approach improves safety even in challenging multi-turn scenarios, suggesting that it can generalize across various harmful contexts. However, while feature steering shows promise in enhancing safety, it also introduces trade-offs, such as increased over-refusal of safe prompts and regressions in overall performance on factual recall and reasoning benchmarks. Thus, while feature steering is a valuable addition to safety mechanisms, it requires careful tuning and consideration of its impact on model capabilities, contrasting with the more holistic but potentially less flexible nature of fine-tuning.
How did the authors validate the proposed method, particularly in terms of the datasets and benchmarks used to measure the effectiveness of feature steering on model safety and performance?
The authors validated the proposed method of feature steering by employing several datasets and benchmarks to measure its effectiveness on model safety and performance. They utilized the WildGuard dataset, which includes human-audited synthetic instruction prompts across various harm categories, to assess single-turn refusal rates for both unsafe and safe prompts. Additionally, they employed the XS-Test benchmark, which evaluates LM refusal behavior with prompts that share surface-level similarities with harmful content, allowing for the measurement of over-refusal. For multi-turn interactions, they used the Crescendo framework, which tests the model's ability to resist adversarial attacks over a series of conversational turns. To evaluate overall performance, they leveraged benchmarks such as MMLU, Truthful QA, and GSM-8K, which assess the model's reasoning, factual recall, and accuracy across diverse topics, thus providing a comprehensive analysis of the impact of feature steering on both safety and performance.
What are some identified limitations of the feature steering method, particularly regarding its impact on model performance and potential trade-offs, as discussed in the paper?
The feature steering method has several identified limitations, particularly concerning its impact on model performance and trade-offs. Firstly, while steering can improve safety by increasing refusal rates for unsafe prompts, it also leads to significant over-refusal of safe prompts, resulting in a higher rate of inappropriate refusals. Additionally, the method causes regressions in overall performance on factual recall and reasoning benchmarks, with no instances of over-refusal found in the tested benchmarks, indicating that the performance drop is not solely due to increased refusals. The paper also notes that the regressions in performance are not localized to potentially triggering topics, suggesting a broader issue with the feature steering approach. Lastly, the authors highlight that the lack of modularity in the features identified may contribute to these performance degradations, indicating a need for further exploration of the interactions between amplified features and naturally activated features.